As you settle into this moment, into the softness beneath you and the quiet around you, let yourself begin to release the day. There is nothing you need to do right now, nowhere you need to be. You are here, and that is enough. In this time reserved just for rest, we are going to travel together through the universe, not with urgency or effort, but with the gentle curiosity of someone drifting on calm waters, watching the stars appear one by one in a darkening sky. The universe is vast beyond comprehension, ancient beyond imagination, and yet it holds you with perfect gentleness. Right now, as you breathe in and out, as your body finds its natural rhythm of rest, you are part of something magnificent. Every atom in your body was forged in the heart of a star that lived and died long before our sun was born. You are made of stardust, and tonight, as you journey towards sleep, you are simply returning to the stillness from which all things came. There is something profoundly peaceful about the universe when we approach it not with the need to understand everything, but with the willingness to simply witness its beauty. The cosmos does not hurry. Galaxies turn over millions of years. Light travels across emptiness for billions of years before reaching our eyes. Everything in the universe moves according to its own perfect time, and tonight, you can move according to yours. There is no rush. There is only this gentle unfolding, this quiet exploration of wonders that ask nothing of you except your presence. So let your eyes grow heavy if they wish. Let your breathing slow and deepen. Let the concerns of the day fade like stars, disappearing into the dawn. We are going to explore the universe together, and as we do, you may find yourself drifting, floating, settling into deeper and deeper rest. That is exactly as it should be. The universe will be here, vast and patient, whether you hear every word or whether you slip away into dreams. Either way, you are held, you are safe, and you are right where you need to be. The gentle enormity of space, when we look up at the night sky, we see points of light scattered across darkness, beautiful and distant, and yet we rarely grasp just how much emptiness lies between them. The universe is not crowded. It is not cluttered. It is, more than anything else, a testament to space itself, to the peaceful expanse of nothing that allows everything else to exist. If you could somehow remove all the matter in the universe, all the stars and planets and galaxies and dust, you would be left with almost exactly the same amount of space you started with. The universe is 99.99999% emptiness, a vast quiet void punctuated here and there by islands of light and matter. This emptiness is not a lack. It is not a failure or an absence. It is the fabric upon which existence is embroidered, the silence between notes that makes music possible. In the space between stars, in the gulf between galaxies, there is a profound peace, a stillness so complete that nothing disturbs it for millions of years at a time. And you, settling now into your own stillness, are participating in this same cosmic quiet. Your body is mostly empty space too, when you consider it at the atomic level. The atoms that make up your skin and bones are themselves tiny solar systems, with nuclei like suns and electrons like planets. And between them, vast proportions of nothing at all. Between the stars, in all that quiet emptiness, there is actually something rather than pure nothing, though it takes sensitive instruments to detect it. The space between stars contains thin wisps of gas, mostly hydrogen, along with dust grains so fine they make flour look coarse by comparison. In some places, this gas and dust gather into clouds that glow faintly with reflected starlight or with their own gentle luminescence. These clouds are called nebulae, and they are the nurseries where new stars are born. But even in these relatively dense regions of space, the matter is so thinly spread that if you were standing in the middle of a nebula, you would not see anything around you except darkness. You would have no sense of being inside a cloud at all. Only from vast distances do these clouds reveal themselves, glowing in colors of red and blue and green, painted across the darkness like watercolors on black paper. In other regions of space, the emptiness is even more complete. Between galaxies, in the vast intergalactic voids that separate one island universe from another, there is almost nothing at all. These voids contain perhaps one atom in every cubic meter of space, sometimes less. To put that in perspective, the air you are breathing right now contains about 25 quintillion molecules in every cubic meter. 25 quintillion compared to 1. The space between galaxies is emptier than the best vacuum we can create in laboratories on Earth. Emptier than anything you can experience in daily life. A silence and stillness and absence so profound that it becomes its own kind of presence. The distance between objects in space is measured in ways that help us comprehend the incomprehensible. Light, which travels faster than anything else in the universe, faster than thought itself, it sometimes seems, moves at 186,000 miles every single second. In 1 second, a beam of light could circle the Earth more than 7 times. And yet, the distances in space are so vast that we measure them not in miles or kilometers, but in how long it takes light to cross them. A light year is the distance light travels in 1 year, and it equals about 6 trillion miles. 6 trillion miles of emptiness crossed at the speed of light, and it takes a full year to do it. The nearest star to our Sun, a star called Proxima Centauri, is 4.2 light years away. When you look at that star, if you could see it with your naked eye, you would be seeing light that left its surface 4 years ago. Light that has been traveling through empty space all that time, crossing distances so vast that human minds can barely hold them. And Proxima Centauri is our neighbor, practically on our doorstep in cosmic terms. Most stars you see in the night sky are hundreds or thousands of light years away. Some of the faint smudges visible through telescopes are galaxies, millions, or even billions of light years distant, so far away that the light reaching us now began its journey before the Earth even existed. This is not meant to make you feel small, though perhaps there is comfort in smallness too, in realizing that your worries are held in a universe so vast that they dissolve like sugar in an endless ocean. Rather, this is meant to invite you into a sense of perspective, into the recognition that you are part of something that operates on scales of time and distance that dwarf every human concern. The universe is patient. It does not rush, and neither must you. And yet, even in these vast voids, the universe is not truly empty. Modern physics has revealed that what we call empty space is actually seething with activity at the quantum level, with particles and antiparticles constantly popping into existence and annihilating each other in time spans so brief they barely count as existence at all. Space itself, the very fabric of the universe, is not a passive stage on which events occur, but an active participant, bending and stretching in response to matter and energy, carrying waves and ripples across cosmic distances. But these are subtleties, quantum whispers in the darkness. For our purposes, as you settle deeper into rest, what matters is the peace of it all, the vast quietness, the sense of space that allows everything to simply be, our own solar system. The small corner of the universe we call home is mostly empty space as well. The sun, massive as it is, containing 99.8% of all the matter in our solar system, is still just a point of light in an enormous volume of darkness. If you could shrink the solar system down so that the sun was the size of a beach ball, the Earth would be a small marble about 100 feet away, and the next planet, Mars, would be another 150 feet beyond that. Jupiter would be over 500 feet from the sun, and Neptune, the most distant planet, would be more than half a mile away. All that space in between would be empty, with just tiny grains representing the asteroids and comets. And even those would be separated by yards or feet of nothingness. This is the universe into which you were born, a universe of profound spaciousness, where matter is rare and precious, where light travels vast distances through peaceful darkness, where time moves slowly and nothing is hurried. As you breathe now, slowly and easily, you can imagine yourself floating in that darkness, weightless and free, with stars scattered around you like fireflies in an infinite garden. There is nothing to hold on to and nothing to fear. There is only the gentle presence of existence itself, the quiet fact of being, suspended in a cosmos that asks nothing of you but allows you to simply rest, to simply be, to simply drift in the vastness like a leaf on still water. The ancient light of stars, every star you have ever seen in the night sky is a sun, similar to our own or vastly different, but always a massive sphere of gas held together by its own gravity and heated by nuclear fusion in its core. Stars are the universe's way of creating light and warmth in the darkness. And they do so not for years or centuries, but for millions or billions of years at a time. Our sun, that familiar presence that rises each morning and sets each evening, has been shining steadily for about 4.5 billion years, and it will continue to shine for about another 5 billion years before its fuel begins to run low. 4.5 billion years of continuous light, of endless energy pouring out into space, warming our world and making life possible. But our sun is middle-aged, unremarkable in the grand catalogue of stars. Some stars are far older, born when the universe itself was young. The oldest stars we know of formed just a few 100 million years after the Big Bang, in an era when the universe was simpler, when it contained mostly just hydrogen and helium, before heavier elements had been forged in stellar furnaces and scattered by dying stars. These ancient stars, called population 3 stars, were massive and short-lived, burning bright and hot before exploding and seeding space with the first metals, the first carbon and oxygen and iron that would eventually become planets and, much later, people. We have never actually seen a population 3 star because they all died long ago. But we see evidence of them in the light of later generations. The universe remembers. Everything that has ever happened leaves traces, and the universe is a vast library of those traces, written in light and shadow, in the composition of distant stars and the patterns of galaxies across space. When astronomers look at the most distant galaxies, galaxies so far away that their light has taken 13 billion years to reach us, they are looking back in time, seeing the universe as it was when it was young, when the first stars were just beginning to illuminate the darkness. This is one of the beautiful paradoxes of astronomy. The farther away you look, the further back in time you see. Light takes time to travel, and while it travels, the universe changes. The galaxies we see in the most distant reaches of space are not as they are now, but as they were billions of years ago. Some of those galaxies may no longer exist in their original form. They may have collided with other galaxies, merged and transformed, or their stars may have lived and died and been replaced by new generations. But the light that left them all those eons ago is still traveling through space, carrying an image of the past, a message in a bottle thrown across the cosmos. When you look at a star, any star, you are seeing the past. The light from the sun takes about 8 minutes to reach Earth. So when you see the sun, you are seeing it as it was 8 minutes ago. If the sun were to suddenly vanish, we would not know for 8 minutes, because the last light it emitted would still be traveling toward us. The bright star Sirius, the brightest star in the night sky, is about 8.5 light years away. So when you see Sirius, you are seeing light that left its surface 8.5 years ago. If you were looking at it tonight, you were seeing Sirius as it was in early 2017. Light that has been traveling through space all this time, through the emptiness between stars, never wavering, never stopping, until finally it enters your eye and creates the sensation of starlight. Some of the stars you can see with your naked eye are hundreds of light years away, and some of the faint ones visible through telescopes are thousands of light years distant. When you look at those stars, you are looking at light that began its journey before recorded history, before civilizations rose and fell, before humans learned to write or farm or build cities. That light has been traveling through space for longer than human memory extends, crossing vast gulfs of emptiness, and now it reaches you at this moment as you settle into rest. There is something deeply moving about this, about the fact that ancient light from distant stars arrives just in time to be seen by you. Here, now, as you prepare for sleep, stars come in many different colors. Though you might not notice this when you look at the night sky with just your eyes. To the unaided eye, most stars appear white or perhaps faintly colored. But when viewed through telescopes or captured in photographs, their colors become more apparent. Some stars are red, cool, and enormous, nearing the end of their lives. Some are blue, hot, and massive, burning through their fuel at tremendous rates. Some are yellow, like our sun, stable and middle-aged, and some are white, small and dense and hot. Either young stars just beginning their lives, or the remnants of stars that have shed their outer layers and are slowly cooling down over billions of years. The color of a star tells you about its temperature. Blue stars are the hottest, with surface temperatures of 20,000 degrees or more. White stars are cooler, around 10,000 degrees. Yellow stars like our sun are cooler still, around 5,000 or 6,000 degrees. And red stars are the coolest of all. Though cool is a relative term when you are talking about an object that is still thousands of degrees. These temperature differences arise from the mass of the star and the stage of life it is in. More massive stars burn hotter and faster, living short, dramatic lives of just a few million years before exploding as supernova. Less massive stars burn cooler and slower, living for tens of billions of years, far longer than the current age of the universe. Our sun will never explode as a supernova. It does not have enough mass for such a dramatic end. Instead, in about 5 billion years, when the hydrogen fuel in its core runs low, it will begin to swell, expanding into a red giant that will engulf the inner planets, possibly including Earth. For a time, it will be hundreds of times larger than it is now. A vast, cool sphere glowing red in the darkness. Then, after a few 100 million years in this bloated state, it will gently shed its outer layers into space, creating a beautiful shell of glowing gas called a planetary nebula, and the core that remains will slowly cool and fade, becoming a white dwarf, a dense ember no larger than Earth, glowing faintly in the darkness for billions upon billions of years. This is the fate of most stars. A long, slow life, a brief period of change, and then an even longer, slower fade into darkness. There is something peaceful about this, about the way stars live out their time without hurry, without panic, simply existing and shining until they no longer can. They do not fight their endings. They do not resist the natural progression of time. They shine, and then they change, and then they rest, and the universe continues, always making new stars from the material of the old, always cycling matter and energy through endless transformations. Some of the most beautiful objects in the universe are the remnants of dead stars. Planetary nebulae glow in colors of green and blue and red, shells of gas expanding slowly into space, illuminated by the ultraviolet light of the white dwarf at their center. They last for only about 10,000 years before the gas disperses and fades, but during that brief time, they are among the most stunning sights in the cosmos, like cosmic flowers blooming in the darkness. The names of planetary nebulae reflect their beauty. The Ring Nebula, the Cat's Eye Nebula, the Helix Nebula, also called the Eye of God. Each one is unique, shaped by the rotation of the dying star and the interactions of stellar winds and magnetic fields. And each one represents the final act of a star that shone for billions of years. As you lie here, breathing slowly, letting your body sink deeper into rest, you can imagine yourself drifting among these nebulae, floating through their glowing gases, surrounded by colors that do not exist on Earth, witnessing the peaceful afterglow of stars that have ended their long lives. There is no danger in this imagining, no heat or cold or radiation to harm you. You are simply a witness, a consciousness drifting through beauty, observing without needing to understand, present without needing to act. The universe unfolds around you in its own time, and you are held gently in the midst of it all, safe and at peace. Galaxies like islands in the dark if. Stars are the cities of the universe. Then galaxies are the continents, vast collections of stars bound together by gravity, spinning slowly through space in structures that can take hundreds of thousands or even millions of years to complete a single rotation. Our galaxy, the Milky Way, contains somewhere between 200 billion and 400 billion stars, a number so large that it loses meaning. But each one of those stars is a sun, and many of them likely have planets. And some of those planets may be home to life, and even if only a tiny fraction of them are, the galaxy is still full of worlds and possibilities beyond counting. When you look up on a clear, dark night, away from city lights, you can sometimes see a faint band of light stretching across the sky, milky and diffuse, made up of countless stars, too distant to resolve individually. That band is the Milky Way, your home galaxy, seen from inside. We live within the galaxy's disk, about 2/3 of the way out from the center, in a quiet region between two of the spiral arms. From our vantage point, when we look toward the galactic core, we see the combined light of billions of stars, all blending together into that soft glow. And when we look in the opposite direction, away from the center, we see fewer stars, the outer edge of the galaxy fading into darkness. The Milky Way is a spiral galaxy, which means it has a flat disk with spiral arms curving out from a central bulge. If you could somehow rise above the galaxy and look down on it from above, you would see those arms, graceful curves studded with bright blue stars, regions of active star formation where gas and dust are collapsing into new suns. The spiral arms are not permanent structures, not solid objects that rotate like the arms of a pinwheel. Instead, they are density waves, regions where stars and gas temporarily crowd together as they orbit the galactic center, creating the appearance of spirals even though individual stars move in and out of the arms over millions of years. At the center of the Milky Way, hidden behind thick clouds of dust that block visible light, lies a supermassive black hole. This black hole, called Sagittarius A*, has a mass about 4 million times that of our Sun, all compressed into a region smaller than our solar system. It sits there, quiet and dark, occasionally pulling in gas and dust that ventures too close, but mostly it simply exists. A gravitational anchor around which the entire galaxy orbits. Stars near the galactic center move incredibly fast, whipping around the black hole at speeds of thousands of kilometers per second, completing orbits in just a few years or decades. Farther out, where we are, stars move more slowly, and our Sun takes about 200 million years to complete one orbit around the galactic center. In all of human history, in all the time that our species has existed, the Sun has moved only about 1/500th of the way around the galaxy. The Milky Way is not alone. It is part of a small group of galaxies called the Local Group, which contains about 80 galaxies in total, most of them small dwarf galaxies that orbit the larger ones. The second largest galaxy in the Local Group is Andromeda, a spiral galaxy somewhat larger than the Milky Way, located about 2.5 million light-years away. Andromeda is the most distant object you can see with your naked eye, a faint smudge of light in the constellation Andromeda, and when you look at it, you are seeing light that left that galaxy 2.5 million years ago, long before humans evolved, when our ancestors were still small, ape-like creatures living in the forests and grasslands of Africa. Andromeda and the Milky Way are approaching each other, drawn together by gravity, and in about 4 billion years, they will collide. This sounds dramatic, but galaxy collisions are actually quite gentle affairs. The stars in both galaxies are so far apart that almost none of them will actually hit each other. Instead, the two galaxies will pass through each other like ghosts, their shapes distorting under the gravitational strain, and then they will fall back together, merging over hundreds of millions of years into a single, larger galaxy. By the time this happens, the Sun will be nearing the end of its life, swelling into a red giant, and if Earth still exists, it will be a barren, lifeless rock baked by the Sun's increasing heat. But the collision of the galaxies will create new bursts of star formation, new regions of bright blue stars forming from the gas and dust stirred up by the encounter, and the combined galaxy, sometimes called Milkomeda or Milkdromeda, will shine on for billions of years after our Sun has faded. Beyond the Local Group, galaxies gather into larger structures. Groups of galaxies cluster together into clusters, and clusters gather into superclusters. Vast filaments of galaxies stretching hundreds of millions of light-years across space. Between these filaments lie enormous voids, regions where very few galaxies exist, vast empty spaces that contain mostly just darkness. The universe at the largest scales looks like a cosmic web, with galaxies tracing out delicate strands and sheets, surrounding great, empty bubbles. A structure that emerged from tiny fluctuations in the early universe. Regions that were just slightly denser than their surroundings, and over billions of years gathered more and more matter until they became the galaxies and clusters we see today. Galaxies come in many shapes. Some are spirals, like the Milky Way, with graceful arms and flat disks. Some are ellipticals, smooth and featureless, shaped like footballs or spheres, containing mostly old red stars and little gas or dust for new star formation. Some are irregular, with no clear structure at all, often the result of gravitational interactions or past collisions with other galaxies. And some are peculiar, strange shapes that do not fit into any neat category. Galaxies caught in the act of transformation, their forms twisted and torn by gravity. One of the most beautiful types of galaxies is the barred spiral. A spiral galaxy with a straight bar of stars running through its center, and spiral arms that emerge from the ends of the bar rather than from the center itself. The Milky Way is actually a barred spiral, though we did not discover this until relatively recently because we cannot easily see the bar from our position within the galaxy. The bar is a gravitational structure that forms when stars in the central regions of a spiral galaxy align in their orbits, creating a temporary concentration that funnels gas toward the galactic center, sometimes triggering bursts of star formation or feeding the central black hole. Some galaxies shine with incredible brightness because of the activity in their cores. These are called active galaxies, and their central black holes are not quiet like Sagittarius A*, but are actively feeding on surrounding matter, pulling in gas and dust at tremendous rates. The material falling toward the black hole forms a disk around it, and as the disk rotates, friction heats it to millions of degrees, causing it to emit radiation across the entire spectrum, from radio waves to gamma rays. Sometimes, active galaxies shoot out immense jets of material from their poles, streams of particles and energy that extend for thousands of light years into space, glowing bright enough to outshine the entire galaxy. The most extreme active galaxies are called quasars, and they are among the brightest objects in the universe. A single quasar can be brighter than 1 trillion suns, all that light coming from a region no larger than our solar system. Quasars were most common when the universe was young, and almost all the quasars we see are billions of light years away, their light reaching us from a time when the universe was wilder and more violent, when galaxies were still forming and colliding frequently, when supermassive black holes were growing rapidly by devouring the matter around them. Today, the universe is calmer, more settled, and active galaxies are rarer, though they still exist, reminders of the energetic past. The process is neither quick nor neat. Planets migrate inward and outward as they interact gravitationally with the disk and with each other. Some planets are ejected from the system entirely, flung out into interstellar space to wander the galaxy as rogue worlds, dark and cold, no longer warmed by any star. Other planets collide, smashing together in impacts that release tremendous energy, sometimes merging into larger worlds, sometimes breaking apart into fragments that eventually reaccrete or are swept up by other bodies. The early solar system was a chaotic place, full of collisions and near misses, and the planets we see today are the survivors, the objects that found stable orbits and remained there, while countless others were lost. Earth itself is the product of such a collision. About 4.5 billion years ago, not long after the solar system formed, a Mars-sized object called Theia crashed into the young Earth. The impact was catastrophic, melting the surface of both bodies and throwing enormous amounts of material into orbit around Earth. That material eventually coalesced into the Moon, which still orbits us today, a reminder of the violent birth of our world. The Moon is slowly drifting away from Earth, moving about 1.5 inches farther from us each year, and in the distant future, it will no longer create total solar eclipses because it will appear too small in the sky to fully cover the sun. But for now, it is there, faithfully orbiting, creating tides and stabilizing Earth's axial tilt, playing a quiet but essential role in making our planet a stable home for life. Planets come in many varieties. There are rocky planets like Earth, with solid surfaces and thin atmospheres, warm enough to have liquid water and complex chemistry. There are gas giants like Jupiter, massive worlds made mostly of hydrogen and helium, with no solid surface, just layers of gas gradually compressed into liquid and then metallic forms deep in the interior. There are ice giants like Neptune, smaller than gas giants, but still enormous compared to Earth, with thick atmospheres rich in water, methane and ammonia, surrounding small rocky cores. And there are countless intermediate types, worlds that do not fit neatly into our categories, planets that challenge our understanding of how worlds form and evolve. As you rest here, you're breathing slow and even. You can picture yourself floating above a galaxy, seeing it whole, seeing the sweep of its spiral arms or the smooth glow of its elliptical form, seeing the millions or billions of stars that make it up, each one a point of light, each one a sun. From such a vantage point, individual stars would be invisible, but their combined glow would create patterns of light and shadow, regions of brightness where stars crowd together, regions of darkness where dust obscures the light. You would see the galaxy rotating slowly, imperceptibly, its motion so gradual that even if you watched for a lifetime, you would detect no change. Everything in the universe moves, but everything moves at its own pace, and there is no hurry, no rush, no urgency. There is only the slow, majestic turning of galaxies in the dark, a dance that has been going on for billions of years and will continue for billions more, long after you and I and everyone we know has returned to stardust. The birth and death of worlds' planets are common in the universe, far more common than we realized even a few decades ago. For most of human history, the only planets we knew about were the ones in our solar system, the 5 visible to the naked eye, plus Earth itself, and later Uranus and Neptune discovered with telescopes, and still later Pluto, small and distant and strange. It was only in the 1990s that we began finding planets around other stars, and since then we have discovered thousands of them, with thousands more candidates waiting to be confirmed. It turns out that most stars have planets, and the galaxy is full of worlds, some like Earth, some utterly alien, but all of them formed through the same basic process, the same gentle collapse of gas and dust into rotating disks around young stars. When a star is born from a collapsing cloud of gas and dust, not all the material falls onto the star. Some of it forms a disk around the star, a flat, rotating structure called a protoplanetary disk. Within this disk, dust grains stick together, clumping into larger and larger objects through collisions and electrostatic forces. Pebbles become boulders, boulders become mountains, mountains become planetesimals, small rocky bodies a few kilometers across. These planetesimals collide and merge, growing into protoplanets. And eventually, after millions of years, the disk clears and a solar system emerges, with planets orbiting the star in stable, roughly circular orbits, each one occupying its own region of space. Some planets orbit their stars very closely, completing an orbit in just a few hours or days, their surfaces baked to thousands of degrees by the intense starlight. These are called hot Jupiters, gas giants that somehow migrated inward from the outer regions where they formed, dragged by interactions with the protoplanetary disk or nudged by gravitational encounters with other planets. Their atmospheres are strange and exotic, with clouds of vaporized metals raining down onto deeper layers, with winds howling at thousands of miles per hour, with daysides hot enough to melt rock and nightsides only slightly cooler. Other planets orbit far from their stars, cold and distant, receiving only a fraction of the light and warmth that Earth enjoys. These worlds are frozen, their surfaces covered in ice, their atmospheres thin or non-existent. Some of them may have subsurface oceans kept liquid by tidal heating from their parent star or from large moons, hidden seas trapped beneath miles of ice, isolated from the universe above but potentially harboring life in their dark, cold waters. Europa, a moon of Jupiter, is one such world, and Enceladus, a moon of Saturn, is another. Both have subsurface oceans, both eject plumes of water vapor into space through cracks in their icy crusts, and both are targets for future missions that will search for signs of life in these hidden seas. The search for life in the universe is one of the great quests of our time, and it begins with the search for habitable planets, worlds where liquid water can exist on the surface. Water is essential for life as we know it, a solvent that allows complex chemistry to occur, a medium in which molecules can move and interact. Planets in the habitable zone, the region around a star where temperatures are just right for liquid water, are prime targets in the search for life. Too close to the star, and water evaporates, leaving a dry, barren world like Venus. Too far from the star, and water freezes, locking the planet in ice. But in the habitable zone, conditions are just right. And if the planet has the right atmosphere and the right geology, water can pool on its surface, creating oceans and lakes and rivers, environments where life might emerge. We have found dozens of potentially habitable planets, though we cannot yet say for certain whether any of them actually harbor life. The distances are too great for us to visit, and even sending signals and receiving replies would take decades or centuries. But we can analyze the light from these planets, looking for chemical signatures in their atmospheres that might indicate the presence of life. Gases like oxygen and methane that, when found together, suggest biological activity. The search is painstaking and slow, but it continues, driven by the profound question of whether we are alone in the universe or whether life has arisen elsewhere, on other worlds orbiting other stars, following its own path of evolution under alien skies. Some planets are truly strange, defying our expectations and expanding our understanding of what a planet can be. There are planets made mostly of diamond, carbon worlds where the intense pressure deep in the interior has crystallized carbon into a solid diamond core. There are planets covered entirely by oceans, with no land at all, just water thousands of miles deep. There are planets that orbit two stars instead of one, their skies lit by twin suns that rise and set in complex patterns. And there are planets ejected from their solar systems, rogue worlds wandering the galaxy in darkness, warmed only by the residual heat of their formation and by the decay of radioactive elements in their cores. Each planet is a world unto itself, with its own history, its own geology, its own weather and climate and chemical cycles. Each planet is a variation on the theme of planetary formation, a unique outcome of the processes that turn gas and dust into solid worlds. And in our own solar system, we have a remarkable diversity of planets, each one offering insights into how worlds form and evolve, each one a laboratory for understanding the universe. As you lie here, sinking deeper into rest, you can imagine yourself traveling from world to world, visiting planets both familiar and strange. You stand on the rusty red surface of Mars, looking up at a sky the color of butterscotch, watching the small, distant sun set behind distant dunes. You float above Jupiter, watching the swirling clouds of the Great Red Spot, a storm larger than Earth that has been raging for hundreds of years. You descend through the thick, orange atmosphere of Titan, Saturn's largest moon, landing on shores of liquid methane, looking up at Saturn itself, hanging huge and beautiful in the sky. Each world is peaceful in its own way, governed by physics and chemistry, shaped by time and chance, existing without need or purpose, simply being what it is. The fabric of space and time, the universe, is not just made of matter and energy. It is also made of space and time, and these are not passive backdrops, but active participants in the cosmic drama. Space can bend and stretch, time can slow down and speed up, and the two are woven together into a single fabric called space-time, a four-dimensional structure that Einstein described in his theory of general relativity. This idea that space and time are flexible and dynamic transformed our understanding of the universe and revealed phenomena so strange that they seem like science fiction. Yet they are real, confirmed by countless experiments and observations. Gravity, in Einstein's view, is not a force that pulls objects together, but a curvature of space-time caused by the presence of mass and energy. Imagine space-time as a stretched rubber sheet, flat and smooth in the absence of matter. Now place a bowling ball on the sheet, and it creates a depression, a curve in the fabric. If you roll a marble near the bowling ball, the marble will curve toward it. Not because the bowling ball is pulling on it, but because the sheet itself is curved. And the marble is simply following the straightest possible path through that curved space. This is how gravity works. The sun curves space-time around it, and the Earth follows that curvature, orbiting not because it is being pulled, but because it is moving along a geodesic, the equivalent of a straight line in curved space. This bending of space-time has observable effects. Light, which always travels in straight lines through space, will follow the curvature of space-time when it passes near a massive object. If light from a distant star passes close to the sun on its way to Earth, the sun's gravity will bend the light's path slightly, making the star appear to be in a slightly different position than it actually is. This effect, called gravitational lensing, was one of the first confirmations of Einstein's theory. Observed during a solar eclipse in 1919, when stars near the sun's edge were photographed and found to be displaced from their expected positions, gravitational lensing is now used as a powerful tool in astronomy. When light from distant galaxies passes through the gravitational field of massive galaxy clusters between them and us, the light is bent and magnified, allowing us to see galaxies that would otherwise be too faint and distant to detect. Sometimes the lensing creates multiple images of the same galaxy, arranged in arcs or rings around the lensing cluster, beautiful patterns called Einstein rings. Other times, the lensing simply brightens the background galaxy, acting like a natural telescope that allows us to peer deeper into the universe than we otherwise could. Time is also affected by gravity. Clocks run slower in stronger gravitational fields, an effect called gravitational time dilation. On Earth's surface, where gravity is stronger, time passes slightly more slowly than it does high above the planet, where gravity is weaker. The difference is tiny, measured in billionths of a second, but it is real and must be accounted for in systems like GPS satellites. which orbit high above the Earth and experience time at a slightly different rate than clocks on the ground. If the satellites did not correct for this time dilation, GPS coordinates would quickly become inaccurate, drifting by several kilometers each day. Near extremely massive or dense objects, time dilation becomes more pronounced. Near the surface of a neutron star, where gravity is billions of times stronger than on Earth, time passes noticeably slower than it does far from the star. And near a black hole, time dilation becomes extreme. As you approach the event horizon, the boundary beyond which nothing can escape, time slows more and more. To someone watching from a safe distance, an object falling toward a black hole would appear to slow down as it approached the event horizon, its light shifting to red and fading away, frozen forever at the edge. But to the falling object, time would pass normally, and it would cross the event horizon in a finite amount of time, unaware that to the outside universe it appeared to stop. Black holes are the ultimate expression of space-time curvature. Regions where gravity is so strong that space-time curves back on itself, creating a one-way boundary that nothing can cross from the inside out. Once you cross the event horizon of a black hole, all paths through space-time lead inward toward the singularity at the center, a point where density becomes infinite and our understanding of physics breaks down. We do not know what happens at the singularity because our theories cease to work under such extreme conditions. But we know that the journey there is brief. Even the largest black holes will crush anything falling into them within seconds or minutes after crossing the event horizon, stretched and compressed by tidal forces so strong they tear apart even atoms. Yet black holes are not cosmic vacuum cleaners, indiscriminately sucking up everything around them. They only affect objects that come very close, within a few times the radius of the event horizon. Farther away, their gravity behaves just like the gravity of any other object with the same mass. If the Sun was suddenly replaced by a black hole of equal mass, Earth's orbit would not change at all. We would lose our source of light and heat, and life would end, but our orbit would remain the same, because gravity depends only on mass, not on whether that mass is a shining star or a dark black hole. Black holes can spin, and when they do, they drag space-time around with them, creating a region called the ergosphere where nothing can remain stationary. Within the ergosphere, space-time itself is rotating, pulled along by the spinning black hole, and anything in that region is forced to rotate with it. This effect, called frame dragging, also occurs around Earth and other rotating bodies, but it is so weak that it took extremely sensitive experiments to detect it. Around a spinning black hole, frame dragging is intense, and it has strange consequences, including the theoretical possibility of extracting energy from the black hole's rotation. Space-time can also carry waves, ripples that propagate outward from accelerating masses at the speed of light. These gravitational waves were predicted by Einstein, but not detected until 2015, a century after his theory was published. The waves detected that year came from the collision of two black holes, each about 30 times the mass of the Sun, orbiting each other and spiraling inward until they merged into a single, larger black hole. The collision released more energy in a fraction of a second than all the stars in the observable universe were emitting during that same time. But the energy was released not as light, but as gravitational waves, ripples in space-time itself. Gravitational waves stretch and compress space as they pass through it, but the effect is incredibly subtle. The waves detected in 2015 changed the distance between objects on Earth by about 1/10,000th the width of a proton, a change so small that it required the most sensitive instruments ever built to measure. Those instruments, called LIGO, use lasers to measure the distance between mirrors suspended in vacuum chambers 4 kilometers apart, detecting changes far smaller than an atomic nucleus. The fact that we can measure such tiny distortions is a testament to human ingenuity and perseverance. And it has opened a new window on the universe, allowing us to observe events that emit no light at all. Since that first detection, we have observed many more gravitational wave events, mostly from colliding black holes, but also from colliding neutron stars, and possibly from other exotic events. Each detection tells us something new about the universe, about the population of black holes and neutron stars, about the behavior of matter under extreme conditions, about the nature of space-time itself. And there is something deeply moving about the idea that the universe is alive with these ripples, these gentle waves passing through us all the time, carrying information about distant cataclysms, connecting us to events billions of light years away. As you rest here, feeling the weight of your body against the bed, feeling the steady rhythm of your breath, you can think of yourself as part of this fabric, this four-dimensional space-time that connects everything in the universe. You are not separate from the cosmos, but woven into it, a pattern in the fabric, a configuration of matter and energy moving through space-time along paths determined by gravity and inertia. The universe holds you, supports you, carries you forward in time, and asks nothing of you except that you exist, that you be present, that you rest when you need to rest and move when you need to move. There is no right or wrong way to be. There is only being itself, the simple fact of existence, and that is enough. The elements and the alchemy of stars, every element in the universe, heavier than hydrogen and helium, was created inside stars, forged in the nuclear furnaces of stellar cores where temperatures and pressures are high, enough to fuse lighter elements into heavier ones. The carbon in your body, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of these were made in stars that lived and died before our sun was born. You are quite literally made of stardust, and this is not a metaphor or a poetic flourish, but a simple fact, confirmed by decades of astronomical research and nuclear physics. In the beginning, shortly after the Big Bang, the universe contained only the 3 lightest elements: hydrogen, helium, and trace amounts of lithium. These elements were created in the first few minutes after the universe began, when conditions were hot and dense enough for nuclear fusion to occur throughout all of space. As the universe expanded and cooled, fusion stopped, and for hundreds of millions of years, the universe remained in darkness, filled with hydrogen and helium gas slowly clumping together under gravity, preparing to form the first stars. When those first stars ignited, they began the process of nucleosynthesis, building heavier elements through fusion in their cores. The simplest reaction is the fusion of hydrogen into helium, the process that powers most stars, including our Sun. For hydrogen nuclei combine, through a series of steps, into one helium nucleus, and in the process, a small amount of mass is converted into energy according to Einstein's famous equation, E equals mc squared. That energy, traveling outward from the core, keeps the star shining and provides the outward pressure that balances gravity, preventing the star from collapsing under its own weight. When a star exhausts the hydrogen in its core, it begins to contract, and the core heats up until it becomes hot enough to fuse helium into carbon and oxygen. This process requires higher temperatures than hydrogen fusion. about 100 million degrees, but massive stars easily reach such temperatures. As the star continues to evolve, it builds up layers like an onion, with different elements fusing in different shells around the core. Helium fuses into carbon and oxygen. Carbon fuses into neon and magnesium. Oxygen fuses into silicon and sulfur, and finally, silicon fuses into iron. Iron is the end of the line for fusion in stars. Fusing iron into heavier elements requires energy rather than releasing it, so once a star's core is made of iron, fusion stops. The core can no longer support itself against gravity, and it collapses in a fraction of a second, falling inward until the nuclei are packed as tightly as in an atomic nucleus. At that point, the collapse halts suddenly, and the infalling material bounces off the rigid core, creating a shock wave that blasts outward through the star. The star explodes as a supernova, one of the most violent events in the universe, briefly shining as bright as an entire galaxy, visible across billions of light-years of space. During the explosion, the intense heat and density create conditions where elements heavier than iron can form. Neutrons, released by the collapsing core, are captured by nuclei, building up heavier and heavier elements through a process called the R process. This is where gold and platinum and uranium come from, forged in the final moments of a star's life and scattered into space by the supernova explosion. The debris from the explosion, enriched with all these newly created elements, mixes with the interstellar medium, the thin gas and dust between stars, and eventually that enriched material collapses to form new stars and planets. Stars and planets that contain the legacy of the stars that died before them. Our solar system formed from such enriched material. The sun and planets contain elements that could only have been created in supernova, which means that before our solar system existed, multiple generations of stars lived and died in this region of the galaxy, each one creating heavier elements and scattering them into space, each one contributing to the chemical richness that eventually made planets like Earth possible. And Earth itself, with its iron core and rocky mantle, with its oceans of water and atmosphere of nitrogen and oxygen, is a monument to those long-dead stars, a collection of atoms that have been recycled through multiple generations of stellar birth and death. Water, that simple molecule made of 2 hydrogen atoms and 1 oxygen atom, contains atoms with different histories. The hydrogen in water is primordial, created in the Big Bang, unchanged for nearly 14 billion years, except for being incorporated into various molecules. The oxygen, on the other hand, was created in stars, fused from helium in the cores of red giants, and scattered into space when those stars shed their outer layers or exploded. When hydrogen and oxygen combine to form water, they are bringing together atoms from 2 different epochs of cosmic history, one born in the first moments of the universe, the other created billions of years later in the heart of a star. The same is true for every molecule in your body, every breath you take, every bite of food you eat. The atoms have histories that stretch back billions of years, journeys that took them from the Big Bang to the cores of stars, to supernova explosions, to interstellar space, to the solar nebula, to the forming Earth, to the oceans and atmosphere and living things, and eventually, through an unbroken chain of chemistry and biology, to you. You are a temporary arrangement of ancient atoms, a pattern that will persist for a few decades before dissolving and reforming into other patterns, other configurations, contributing your atoms to the ongoing cycle of matter through the universe. There is something deeply peaceful about this perspective, about recognizing that you are not separate from the universe, but a part of it, made of the same stuff as stars and planets and galaxies. The distinction between you and the rest of the cosmos is real, but also somewhat arbitrary, a matter of where you draw the boundary. The atoms in your body were once part of other people, other animals, other plants, scattered across the earth and incorporated into living things through the cycles of birth and death, growth and decay. And before that, they were part of the earth itself, and before that, part of the solar nebula, and before that, part of the interstellar medium, and before that, part of stars, a continuity of matter extending back to the beginning of time. Elements have personalities, in a sense, properties determined by their atomic structure that make them behave in characteristic ways. Carbon is versatile, able to form complex molecules with itself and other elements, the basis of all known life. Oxygen is reactive, eager to combine with other elements, releasing energy in the process, powering the metabolism of most organisms on Earth. Iron is sturdy and abundant, forming the cores of rocky planets and the basis of technologies that shaped human civilization. Each element plays its role in the cosmic drama, contributing to the richness and complexity of the universe. Some elements are rare, created only in specific conditions or through specific processes. Gold, for instance, is rare because it is created only in the most violent events, supernova explosions and the collisions of neutron stars, and even then, it is produced in tiny amounts compared to lighter elements. The gold in a wedding ring or a coin represents atoms that were created in such an event, perhaps billions of years ago, perhaps in a different part of the galaxy, atoms that traveled through space until they were incorporated into the dust cloud that became our solar system, and eventually into the Earth, where they were concentrated by geological processes and mined by humans and shaped into objects of beauty and value. The universe is an alchemist, transforming hydrogen into all the other elements through nuclear reactions in stars, creating the chemical diversity that makes planets and life possible. And this alchemy continues, constantly, as new stars form and old stars die, as matter is cycled through stellar furnaces and scattered back into space, as the universe enriches itself generation by generation, increasing the abundance of heavy elements and creating more and more complex chemistry. In the early universe, planets like Earth could not have formed because there were not enough heavy elements. But over billions of years, as stars lived and died, the universe created the conditions for rocky planets, for water, for the complex chemistry of life. As you lie here, breathing slowly, your body relaxed and still, you can think of the atoms that make you up. Imagine their long journeys from the Big Bang to this moment, from stars to space to Earth to you. They have been part of countless other things, and they will be part of countless things after you are gone. But right now, they are you, arranged in this particular pattern, experiencing this particular moment. And in this moment, there is peace, there is rest, there is the simple presence of being, atoms organized into consciousness, matter aware of itself, the universe experiencing itself through you, the deep past and the beginning. The universe has not always existed, at least not in its current form. About 13.8 billion years ago, space and time and matter and energy all came into being in an event we call the Big Bang. Though that name is somewhat misleading, it was not an explosion in space, but an expansion of space itself, a sudden appearance of the universe, from a state of infinite or near infinite density and temperature, expanding and cooling, evolving through distinct phases as the fundamental forces and particles took the forms we recognize today. In the first fraction of a second, the universe was unimaginably hot and dense, far beyond anything we can create in laboratories, or even fully describe with our current theories. The four fundamental forces we see today, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single force, and particles as we know them did not yet exist. As the universe expanded and cooled, the forces separated one by one, and particles began to form. First quarks and electrons, then protons and neutrons as quarks combined, and finally, a few minutes after the beginning, the first atomic nuclei as protons and neutrons fused in the hot, dense conditions. For the next several 100,000 years, the universe was a hot, glowing fog of hydrogen and helium nuclei and free electrons, opaque to light because photons constantly scattered off the electrons. But as the universe continued to expand and cool, the temperature eventually dropped low enough for electrons to combine with nuclei and form neutral atoms. This moment, called recombination, occurred about 380,000 years after the Big Bang, and it transformed the universe from opaque to transparent. Photons that had been constantly scattering off free electrons were suddenly free to travel through space, and the universe filled with light. That light is still traveling through space today, stretched to longer wavelengths by the expansion of the universe, and we observe it as the cosmic microwave background, a faint glow coming from all directions in space, the afterglow of the Big Bang. The cosmic microwave background is the oldest light in the universe, and it carries information about the conditions in the early universe, tiny variations in temperature and density that were the seeds of all structure, the slight overdensities that would grow over billions of years into galaxies and clusters and superclusters. After recombination, the universe entered a period called the Dark Ages, a time when the universe was filled with neutral hydrogen gas, but no stars had yet formed to light it up. The universe was dark, illuminated only by the fading glow of the cosmic microwave background, cooling and expanding, waiting for gravity to pull matter together into the first structures. Over millions of years, the slight overdensities in the gas grew, pulling in more and more matter, until finally, about 100 to 200 million years after the Big Bang, the first stars ignited, ending the Dark Ages and beginning the era of ionization. These first stars were different from stars today, massive and metal-free, made only of hydrogen and helium. They burned bright and hot, and their ultraviolet light ionized the hydrogen gas around them, creating bubbles of ionized gas that expanded and merged until the entire universe was rionized, transformed from neutral to ionized once more. These first stars also lived fast and died young, exploding as supernovae after just a few million years, scattering the first heavy elements into space and paving the way for later generations of stars and planets. The universe has been evolving ever since, growing more complex and structured, forming galaxies and clusters, stars and planets, eventually life and consciousness. The story of the universe is a story of increasing organization, of matter clumping together under gravity, of energy being concentrated and then dispersed, of simple becoming complex through the interplay of physical laws operating over vast spans of time. And through it all, the universe has been expanding, carrying galaxies away from each other, stretching space itself, making the universe larger and less dense with each passing moment. This expansion was discovered in the 1920s by Edwin Hubble, who observed that distant galaxies were moving away from us, and that the farther away they were, the faster they were receding. This observation led to the realization that the universe is not static, but dynamic, growing over time, and it raised the question of whether the expansion would continue forever, or whether gravity would eventually halt it and cause the universe to contract back into a big crunch, a reverse of the Big Bang. For decades, astronomers worked to measure the rate of expansion and the density of matter in the universe, trying to determine the ultimate fate of the cosmos. The answer came in the late 1990s, and it was a surprise. Not only is the universe expanding, but the expansion is accelerating, getting faster over time. This acceleration is driven by something we call dark energy, a mysterious form of energy that fills all of space and exerts a repulsive force, pushing galaxies apart. We do not know what dark energy is, whether it is a property of space itself, or some exotic field or something else entirely. but we know it exists because we can see its effects on the expansion of the universe. Dark energy makes up about 68% of the total energy content of the universe, far more than ordinary matter, which makes up less than 5%. The rest, about 27%, is dark matter. Another mysterious substance that we cannot see directly, but whose gravitational effects are visible in the motions of galaxies and the bending of light. Dark matter does not emit or absorb light, does not interact with electromagnetic radiation at all, but it has mass and therefore exerts gravitational force, holding galaxies together and shaping the large-scale structure of the universe. In a sense, we live in a universe we barely understand. 95% of the universe is made of dark matter and dark energy, substances we have never detected directly, and we have only indirect evidence for their existence. The ordinary matter we are made of, the atoms and molecules and radiation that make up stars and planets and people, is a tiny minority, a small addition to a universe dominated by invisible substances we are only beginning to explore. And yet, despite this ignorance, we have learned an astonishing amount about the universe, about its age and size and composition, about its history and evolution, about the laws that govern it. We have traced the universe back to a fraction of a second after the Big Bang, understanding how particles formed and how forces separated, how the first nuclei fused and the first atoms combined. We have watched the universe grow and cool and organize itself, forming structures on every scale, from planets to galaxy superclusters. We have seen light from the edge of the observable universe, from galaxies so distant that their light has been traveling toward us for most of the age of the universe. The observable universe, the region of space from which light has had time to reach us since the Big Bang, is vast but finite, with a radius of about 46 billion light-years. This is larger than you might expect, given that the universe is only 13.8 billion years old, but the difference is due to the expansion of space. Light from distant galaxies has been traveling for billions of years, but in that time, space has expanded, carrying those galaxies even farther away, so that they are now much more than 13.8 billion light-years from us. Beyond the observable universe, space continues, possibly forever, filled with more galaxies and stars and planets, regions of the universe we will never see, because the light from them has not had time to reach us, and due to the accelerating expansion, never will. There could be infinitely more universe beyond what we can observe, or the universe could be finite but unbounded, curved back on itself so that if you traveled in one direction long enough, you would eventually return to where you started. We do not know which is true, and we may never know, because the answer lies beyond the reach of our observations. As you rest here, your mind perhaps drifting, perhaps still alert, you can think of the universe stretching out in all directions, vast and ancient, filled with wonders visible and invisible, known and unknown. The universe holds mysteries that may never be solved, questions that may never be answered, but that uncertainty is not a cause for anxiety. It is, instead, an invitation to wonder, to humility, to the recognition that there is always more to learn, always more to discover, always more depth to existence than we currently understand. And in the face of that vastness and that mystery, the best response is not fear or frustration, but quiet awe and the peaceful acceptance that some things are beyond our grasp, and that is perfectly fine. The eternal cycles and the long future. Nothing in the universe is permanent. Stars are born and stars die, galaxies collide and merge, even space itself is changing, expanding, carrying everything apart. But within this constant change, there are cycles, patterns that repeat, processes that turn endings into new beginnings. Matter is never truly destroyed, only transformed, rearranged, recycled through the cosmos in an eternal dance of creation and dissolution. When stars die, they return their matter to space, enriching the interstellar medium with the heavy elements they created during their lives. That enriched gas eventually collapses to form new stars, new planets, new opportunities for complexity, and perhaps for life. The cycle continues, generation after generation, each one building on the legacy of the previous one, each one adding to the chemical richness of the universe. And within this cycle, matter moves from simple to complex and back to simple again, from hydrogen gas to stars to heavy elements, to planets, to living things to dust and gas once more, ready to begin again. On Earth, we see similar cycles on smaller scales and shorter timescales. Water evaporates from oceans and lakes, rises into the atmosphere, condenses into clouds, and falls as rain, returning to the oceans and starting the cycle again. Carbon moves from the atmosphere into plants through photosynthesis, from plants into animals that eat them, from animals back into the atmosphere through respiration or decomposition, a continuous flow of matter through living systems and back to the non-living world. These cycles are powered ultimately by the sun, which provides the energy that drives weather and climate and life. Energy that originated in nuclear fusion deep in the sun's core and traveled through space for 8 minutes before reaching Earth and powering the cycles that sustain us. The universe itself operates on cycles, though they play out over timescales almost incomprehensible to human minds. Stars form, live, and die over millions or billions of years. Galaxies collide and merge over billions of years, creating new structures and triggering new waves of star formation. Even the universe as a whole may be cyclic, though this is speculative. Some theories suggest that the Big Bang was not the beginning of everything, but just the most recent in a series of cosmic cycles, expansions and contractions, or transformations from one state to another. A universe that has no ultimate beginning or end but simply is, eternally changing, eternally existing in some form or another. In the ultimate end, the universe may become a cold, dark, almost empty expanse with particles and radiation spread so thinly that they rarely interact. A state of maximum entropy where nothing changes anymore because there is no energy left to drive change. This fate, sometimes called the heat death of the universe, is the natural consequence of the second law of thermodynamics, which states that entropy, disorder, always increases in a closed system. The universe has been moving toward this state since the beginning, and if current understanding is correct, it will reach it eventually, after an inconceivably long time. But even this grim picture contains elements of beauty and peace. The universe will not end in violence or catastrophe, but in a gentle fading, a slow settling into equilibrium, a return to the stillness from which it emerged. And perhaps even in that far future, in that cold, dark universe, there will be rare fluctuations, quantum events that create brief sparks of order in the surrounding chaos, temporary islands of complexity in an ocean of entropy. The universe may not be capable of dramatic change anymore, but it will still exist, still be, and in some philosophical sense, that is enough. Of course, all of this is speculation based on our current understanding, and our understanding could be wrong or incomplete. There is much we do not know about dark energy, about the ultimate fate of matter, about whether the laws of physics themselves might change over time. The universe has surprised us before, revealing phenomena we never anticipated, and it may surprise us again. Perhaps the universe is stranger and more wonderful than we imagine, with possibilities we have not even considered. The far future of the universe, at least as we currently understand it, is one of increasing emptiness and cold. As the expansion accelerates, driven by dark energy, galaxies will move farther and farther apart, until eventually, all galaxies except those in our local group will have receded beyond the cosmic horizon, their light redshifted to infinite wavelengths, invisible and unreachable. The universe will appear empty except for the stars in our own galaxy, and the few nearby galaxies bound to us by gravity. Even those stars will not last forever. Star formation requires gas and dust, and over trillions of years, that gas and dust will be exhausted, locked up in dead stars and planets, no longer available to form new stars. The last stars will flicker out, the universe growing darker as one by one the lights go out. First, the massive, bright stars will die, then the medium-sized stars like our sun, and finally, over timescales of tens of trillions of years, even the smallest, dimmest red dwarf stars will exhaust their fuel and fade away. The universe will be dark, filled with dead stellar remnants, white dwarfs, neutron stars, black holes, cold and lightless. But even then, change will continue, just much more slowly, over unimaginable spans of time, perhaps 10 to the 100 years or longer. White dwarfs will slowly cool to the temperature of space, becoming black dwarfs, cold spheres of carbon and oxygen drifting through the darkness. Protons, the building blocks of atoms, may decay over timescales of 10 to the 34 years or more, causing even dead stars and planets to slowly dissolve into radiation and lighter particles. And black holes, which seem eternal, will gradually evaporate through a process called Hawking radiation, emitting particles and energy over timescales that depend on their mass, with stellar mass black holes taking 10 to the 67 years to evaporate and supermassive black holes taking 10 to the 100 years or more. What matters, as you lie here in the quiet darkness, is not the ultimate fate of the universe billions or trillions of years in the future, but the present moment, this moment, the simple fact of your existence here and now. The universe may last forever, or it may end someday, but you are here now, breathing, resting, part of the ongoing story of the cosmos, a brief but real expression of matter, organizing itself into consciousness and awareness. You are a way for the universe to know itself, to experience itself, to witness its own beauty and complexity. And in this moment, there is nothing you need to do, nothing you need to achieve. You are enough, exactly as you are, a temporary pattern in the eternal flow of matter and energy, a wave on the surface of the cosmic ocean, rising for a moment, and then subsiding back into the whole. There is peace in this recognition, in the acceptance that you are both insignificant and profoundly significant, both a tiny speck in an incomprehensible vastness, and a unique, irreplaceable expression of existence itself. As our journey through the universe draws to a close, as the images and ideas we have explored begin to fade like stars into the dawn, you can let yourself settle even more deeply into rest. Let go of any thoughts that remain, any questions or curiosities or concerns. They will be there tomorrow if you need them, but right now, there is only rest, only stillness, only the gentle dissolution of waking consciousness into the peace of sleep. The universe will continue without your attention. Stars will shine, galaxies will turn, planets will orbit their suns, all following the laws of physics, all moving through their ancient cycles. And you too are part of those cycles, your body following its own rhythms, your breath slowing, your heart beating steadily, your cells carrying out their quiet work while you sleep. You do not need to control any of this. You do not need to think about it. Your body knows what to do, and the universe knows what to do, and everything will unfold as it should. Feel the weight of your body sinking into the bed. Feel the softness beneath you supporting you completely. Let your muscles relax. Let tension drain away. Let your mind grow quiet and still. There is nothing to hold on to, and nothing to push away. There is only this moment, this breath, this gentle fading of awareness as sleep approaches. You are safe, you are held, you are part of something vast and beautiful and enduring. The same matter that makes up your body has been part of the universe for billions of years, and it will continue to be part of the universe for billions of years more, always changing form, but never truly disappearing. You are temporary, but you are also eternal, a wave that rises and falls but is always part of the ocean, always connected to the whole. Let yourself drift now, like a leaf on still water, like a cloud dissolving into sky, like starlight fading into the glow of dawn. Let the universe carry you gently into sleep, into dreams, into the quiet darkness where consciousness rests and renews itself. There is no effort required, no path to follow, no destination to reach. There is only letting go, releasing yourself into the natural flow of rest, trusting that sleep will come when it comes, and that whether you are awake or asleep, you are held by the universe with perfect gentleness. The stars are shining in the darkness. The galaxies are turning in the void. Space is expanding, carrying everything forward in time. And you, here in this small corner of the cosmos, in this quiet moment, are part of it all, woven into the fabric of existence, made of stardust and ancient light, resting now, finding peace, drifting gently into sleep. Good night. Rest well. The universe will be here when you wake, vast and patient and beautiful, waiting to welcome you into a new day,